Welcome everybody. My name is Maria Kosche, and in this talk my colleague Tore Koss and I are going to introduce an optimal solution to a long-standing open problem related to Simon's congruence. The title of our corresponding paper is Efficiently Testing Simon's Congruence, and is a collaboration with Paweł Gawrychowski from the University in Wrocław and these four from University in Göttingen. Let's start with some basics to develop a conception of today's topic. So here we see a word W, or in other words, a sequence of some letters, from which we can derive several subsequences. A subsequence can be obtained by erasing some letters from the original word. As you can see, we have here several examples for subsequences of the word W. They don't have to start on position 1, and they can be of arbitrary length. But it's very important that the order of letters can't be mixed up. So ABC, for example, is not a subsequence, since we do not have the letters A and B in correct order appearing before the only C in the word. Subsequences are sometimes also called scattered factors and can be formally defined like this. Here we call a subsequence of length k of the word W if there exist positions I1 to Ik such that exactly these positions build up the subsequence W prime, and the order is important in this case, of course. Additionally, a set of subsequences of length k is here subscript k from starting position I in the word W, and this denotes the set of subsequences of length k of the word I to n, or the suffix starting on position I inside of the word W. Accordingly, the set of subsequences of length k of the entire word W will be denoted by subscript k IW, because we then start on position 1 in our word W. So here we have a small example. We want to have all the subsequences of length 2 inside of the word ABACA, starting from position 1, so for the whole word. And as we can see here, the subsequences are AA, AB, AC, BA, BC, and CA. So CB, for example, is not possible because the B occurs before the C in this word. So the set of possible subsequences is now a very basic element when we look at the definition of Simon's congruence. We say that two words W and W prime are equivalent under Simon's congruence sum k if the set of possible subsequences of both words is the same. As an example, we take these two words here, and the sets of subsequences of length 2 of these two words are like this. And as we can see, they are the same. So these two words are indeed sim2 equivalent. When we look at the same two words again, but consider the set of possible subsequences of length 3 now, then we can see that we can build the subsequence BBB out of the word W prime, but not from W. So as we can see, here are only two B's, so it's really not possible that we can find the subsequence BBB inside of this word, but we can inside of W prime. So these two words are not sim3 equivalent. Additionally, we say that BBB in this case is a distinguishing word of length k, as it occurs only in one of the subset sets of our example words. After considering examples where two words are equivalent under Simon's congruence, we can also consider the equivalence of different suffixes of the very same word. So if we take two positions ij inside of W, we define that I is sim k equivalent to j if the suffixes starting on position I and on position j are sim k equivalent. And then we say that the positions I and j are k equivalent. So we only look at the word W now and take two suffixes from it. One we take from starting position 2 and the other one from starting position 3, which makes the words BACAB and the word ACAB. The two suffixes are definitely Sim1 equivalent as both contain the letters A, B, and C and no other letter. So these are exactly our subsequences of length 1. But the two suffixes are not Sim2 equivalent as we cannot build, for example, the subsequence BB in the suffix starting on position 3. After all these examples, we come to the definitions of our two main problems covered in our paper. This is on the one hand the decision problem SimK, where we decide whether two words S and T are equivalent under Simon's congruence SimK for a given K. And on the other hand, this is the problem maximK, where the goal is to find the maximum K such that the two input words are equivalent under Simon's congruence SimK. These problems are associated with a long line of research which originates in the PhD thesis of Imre Simon in 1972. There he introduced the notion of Simon's congruence, and there's a long history of algorithm designs and improvements, and so far a paper published in the DLT conference gives us an optimal linear time algorithm for SimK and an O of n log n time algorithm for maximK. One very delicate detail is the fact that Simon claimed to have a linear time solution for maximK in 2003, but the corresponding result was never published. Although Simon indeed might have had an algorithm, we don't know about it. Nevertheless, today we are going to discuss this long open problem maximK and introduce an optimal linear time algorithm using a new data structure called Simon tree. For this data structure, we are going to make usage of Simon's congruence and define equivalence classes according to the equivalence of suffixes of one word. And my colleague Tore will now explain how this works exactly.
Okay, thank you, Mia. We will have a closer look now at the equivalence classes inside each word. That is, first of all, we compare two positions, I and j, with I smaller j. And we will have a look at the subsequences, sets of subsequence corresponding to I and j. First, we note that if j is larger than I, then the subsequences that start at position j or later are contained in the set of subsequences which start at position I or later. So if we additionally let these two sets be equal, then we can say, well, this set in the middle will be equal to, so all positions between I and j will be in the same equivalence classes of I and j. Okay, that is, the equivalence classes are contiguous, and hence we allow ourselves to call them blocks or even K blocks. Then the next important part is that if we have two positions which are K plus 1 equivalent, then by definition they are also K equivalent. Hence, we have the K plus 1 equivalency is a refinement of the K equivalency. Okay, the last important notion is the one of the splitting position. We will just call the rightmost position of each block its splitting position, because well, this is the position because of which we split the block from the rest. Now I will show you how we can find the splitting positions. Of course, we'll start with the one splitting positions, and these are rather easy to find because subsequences of length 1 are basically letters, and we only have to check for at each position if we have seen this letter before or if we haven't. So let's take an example word, bearbeiter. We will go through this word right to left, and whenever we find a letter we haven't seen before, we will mark it as a splitting position. Okay, this begins with the A on the rightmost position, and then we continue with the D. The A on the next position, well, we have seen that before, so we skip it, but the B is also a new letter. Then the last letter we will find will be the C on position 3. So these are all our one splitting positions. Now we can split this word into its one blocks, then it will look like this. And these are the one blocks. Okay, Now the interesting part is how to find the two blocks. For every k, let's assume we already have calculated for k, we take any block, we ignore its splitting position, and then we go through the rest and do the same procedure again, okay? So that is, look at the BAAB here in the middle. We will not care about the B here, and then we will go through the rest, the BAA, again, right to left, and whenever we find a letter we haven't seen before, we will mark it as a 2 splitting position. This will be the A. The A here is old one, and we also have the B here on the left side. And for the other blocks, we do the same procedure. Okay, so now we have the 2 blocks here, and again, to find the 3 blocks, we do the same procedure again. We only have one 2 block which has length more than 1, so length 1 means we can't split anymore because, well, what is there to split? But this 2 block will also be split into 3 blocks. And here we have all our 3 blocks. Now, if we arrange them in an interesting manner, like this, from top to bottom, well, maybe you can already see a tree, which is our aim to build for. One part is that I said when we have a block which already only consists of one position, then this position will, of course, for every k be the same block, right? Because, well, we have one position, and this one position is always equivalent to itself, regardless of how large the k is. So we are able to continue this this tree indefinitely, but we don't really care for all those nodes. That is, we will phase out every child of a singleton block. Okay, then it will look like this. And now this is looks even more like a tree structure. And now Mia will tell us how we can construct this tree in linear time.
Yeah, thanks again. We saw now how a word can be partitioned into blocks of starting positions with regard to the Simon equivalence of suffixes of a word starting on these positions. On our road to examine the equivalence of 2 words, we transform the blocks we see here into a tree data structure. And for our tree, each level shall correspond to 1 row of blocks. The Simon tree is defined to be a rooted ordered tree. So the root corresponds to the 0 block of W, which is the word W itself. The children of a node or a block correspond to the blocks obtained by refinement, as we already saw that here in the block rows. And as Tore already mentioned, the implicit blocks, we conclude that nodes that represent a singleton block with only 1 letter have no children. So there are no further singleton blocks coming from other singleton blocks. Yeah, and I will now give a rough explanation of how to construct a Simon tree efficiently in linear time, followed by a construction example. And if you want to see a more detailed description, including some pseudocode, you can see, of course, in our paper. So in general, we construct the Simon tree from right to left, as we also traverse the input word from right to left. For people who are familiar to it, this works very similar to the construction of a Cartesian tree. And when we are considering a new position now that is to be inserted into the tree, we compute the level where the new position should be placed. This means we have to find out if a letter is, for example, a 1 splitting or a 2 splitting position. This can be done actually by looking at the nodes that are already existent in the tree, but we will assume now that we already know on which level we have to insert a new position. And if you want to see how this works, you can refer to our paper. So during the process, we move up the leftmost branch of the tree, as this is the only branch where our new position can be inserted into our ordered tree. And during this traversal, we close so far open blocks until we reach the correct level and then insert our letter as the leftmost child on its corresponding level. Yeah, we will now see an example. You still remember this beautiful Simon tree here. And we already assumed that we processed positions 5 to 10. So we are only missing positions 1 to 4, which are here the first 4 letters, B, A, C, B, that we want to insert into this tree. Yeah, and we do so, as I already mentioned, by going up the leftmost branch from bottom to top, and we will insert the letter at the correct level where that letter should be. We still remember that this B was a 2-splitting position, so we have to insert it into the second level. And when we go up now here from the bottom, we will first encounter this node. It's on level 3, and we close it. We close it, and we go then up to the next level where we have to insert the node, and we will insert it exactly on this level as a leftmost child to the last parent node on the next level. So we will close this node here, and of course we will conclude that it has the positions 5 and 6, as these are the children that this block has. And then we will insert our new letter here at the next position on the leftmost child position here on level 2. For the next letter, which is the C, it's a 1-splitting position. So we can close this node, and we add the letter C at the leftmost child on level number 1. And we can continue with the last 2 letters, or in this case with the first 2 letters, and insert them here. So, and at the very end, we of course just close the leftmost branch. Very good. So this is how we construct our tree, and as I already said, more details can be found in the paper. Yeah, as a reminder, we already have a structure representing the equivalence classes for one word, the Simon tree, but our main problem is maxim k, where we want to compare 2 words with each other and find the maximum k so that the 2 input words S and T are k equivalent. So now I'm passing the microphone again to Tore so that he can tell you how we can connect the Simon trees of 2 words to solve our problem maxim k.
Yes, thank you. We'll start, of course, by building the 2 trees corresponding to the words S and T, respectively, and then connect the nodes of these trees by a special connection we have called Simon connection, or for short we call it S connection. The S connection is basically just an extension of the Simon equivalence itself, but now we compare 2 blocks of a block of one word with another block of the other word. But we do it the same way by saying that the suffix starting at any position inside of one block should be k equivalent to the suffix starting at any position of the other block. Okay, to calculate this connection, this is a little too complicated. That is, therefore, we start with an easier connection. We call it the P connection or potential connection, and this is quite easy because we start with the 0 nodes. Those are always p-connected, and then if we enumerate the children of any node from right to left, we give the ith child of one node, of one p-connected node, a connection to the ith child of the other p-connected node. And these are all the p-connections we have. And well, let's see how this will look. Okay, we have 2 trees here, the one of a cap and the one of a kappa, and we have moved them a little bit, so the rightmost position of any of these words will now be the uppermost position. Okay, now we start. We have the roots will be p-connected, but we don't show that, and we will continue. We have the uppermost child of a cap will be p-connected to the uppermost child of a kappa, and so will their respective lonely childs. Okay. Then we will proceed through the rest of the tree and always connect the ith child with the ith child. This will in the end look like this. Okay. Now we have the p connection and we want to refine it to an S connection, and for this we have a little criterion. Looks like this. If we have 2 S connected nodes, A and B, and we have two p-connected children of these nodes, a prime and b prime. Then a prime and b prime will be split exactly if we find the letter x such that the suffix starting after the next occurrence of this letter is not k equivalent to well, the suffix in the other word starting after the next occurrence of this letter x. Okay, now we still have this tree with its respective p connections, and we will look at these p connections to try to split them. We start at the top here at the B at position 4. Well, on level 1 we still do the simple letter counting trick, and we look at the letters starting at position 4. We have only a B here on the left side. On the right side we only have an A. Well, A and B are not the same letter, so we can split these two nodes. In the next step we have their children. These will be split as well because, well, they are children of not connected nodes. They are not connected. Okay, we continue with the A on position 3 and the block ABB on position 3 and 5. Again, we have level 1, so we only need to count letters. In this case, we have AB on both cases, so we keep this connection. Next, we look at its rightmost or uppermost child. This will be the A again on node 3, and on the other side we only have the B on position 5. Here we can finally use our criterion, that is, we look for a letter. Let's choose the letter B. If we do that, we start here at position 3, find the letter B. This will be here on position 4, and we look at the suffix starting after that. Well, this is, unfortunately, this is the empty suffix. It's an empty word, and we only have the empty string here as subsequences. Okay, on the other side, if we here start at position 5, look for a B, well, we have a B on position 5, so we find it here, and we look at the suffix starting on the next position. This will be here, and the suffix will only be A. And the suffix has one substring, namely A. So these are not one equivalent, and hence we can split these two blocks of position 3 or position 5 respectively. Okay, next trick, next node is again the AC here. We have level 1, we can count letters, will be ABC in both cases, so we don't need to split here. Okay, but there are children again. In both cases we can do the same. We look again for the letter B, and in both cases we will find on the left side again the B on position 4, and +1 will have the empty suffix, and on the other side we will find a B here on position 4, at 1 will be on position 5. We have the suffix BA, and of course we have substrings of length 1 will be A and B, hence the sets are not equal, hence these nodes will be split, this one and also this one. The only thing left is the respective children of the A or C on position 1 and 2. Well, we had this situation, they will just be split because their parents are split. And now we have all the remaining S connections here to be seen. And now to determine the maximum K on which, for which these two words are K equivalent, we just look at the nodes, all the nodes which contain the position 1 of both words. And then the maximum K for which both words are K equivalent is the maximum level on which these nodes containing position 1 are still S connected. In this case, here on level 1. So these two words are 1 equivalent. Okay, we can also find a distinguishing word by, well, this is a little more complicated. We have, of course, we have described this in our paper, so have a look if you're interested. And two things I haven't mentioned yet, that is, haven't achieved linear runtime yet. We have two tricks to do. The first one is, you may have noticed that whenever we split any block here on level 2, we found a letter B that such that the criterion is broken. Okay, so instead of looking at this node, finding a letter B and then looking at this node, again finding a letter B and looking at this node, finding a letter B. We can just say whenever we read this letter B here, or in the beginning when we read this letter B here, we can just determine which nodes will be split by that. Okay, and then just remember that and split them accordingly. This is a little faster, but unfortunately still not enough. To update this tree, we use these interval union find and split find data structure, which will again speed up a little bit the process. Okay, this is all. Thank you for listening.
And if you are interested in more details, you can always refer to our paper, which is also available as a full version on arXiv. And now we wish you a nice day. Goodbye.
Bye.